In engineering, speed is rarely the biggest challenge. The real enemy is the air itself.
In 1989, Japan's famous Shinkansen bullet trains hit a hard physical limit. They wanted to go slow. Whenever the trains pushed past 160 miles per hour, the real nightmare began when these trains entered tunnels. At those speeds, the train acted like a giant piston inside.
It tightly compressed the air inside, creating an atmospheric shock wave that traveled ahead of the train like a bullet. When that compressed wave hit the tunnel exit, it expanded instantly. The result was a devastating explosion of sound. This wasn't just a loud noise. It was a physical sonic boom that shattered residential. Japan had strict environmental laws. If the engineers couldn't silence the boom, the future of high-speed rail was dead. The engineering team, led by Eiji Nakatsu, was completely stumped. Every aerodynamic shape they tried. The physics seemed impossible. How do you move that much mass through a confined space without compressing the air? The answer didn't come from a supercomputer. It came from a weekend hobby. Nakatsu was an avid bird watcher. He remembered a specific bird he had observed, the Kingfisher, a creature that survives by diving from the predators. Think about the physics here. The bird travels from air, a low-density medium, into water, yet the Kingfisher enters the water effortlessly, without making a single splash. Nakatsu believes the secret lay in the precise geometry of the bird's beak. It was a perfect evolutionary wedge. He wondered, what if a train could enter a tunnel the exact same way a kingfisher enters the water? The team immediately went to work, conducting wind tunnel tests with scale models modeled after the bird's uppering.
The data was staggering. The air pressure didn't build up in front of the model, it parted perfectly around it.
They had discovered biomimicry, the practice of looking to nature to solve complex human engineering problems. In 1997, the newly redesigned 500 series Shinkansen rolled out onto the tracks. And the new nose was a literal replica of the Kingfisher's beak, stretching out over 15 meters long. When it reached full operating speed, the train didn't push the air into a wall anymore. It gently sliced through it. The results exceeded every mathematical projection. The terrifying tunnel boom was completely gone. But eliminating the noise was just the beginning. The new aerodynamic design dropped air resistance by 30%. This massive drop in friction meant the train required 15% less electricity to run at the exact same speeds. And because it was so efficient, Japan was able to increase the speed to 300 kilometers per hour, making it one. Passengers noticed a completely smooth ride. The cabin was quieter, the vibrations vanished, and the efficiency skyrocketed. The Shinkansen became a global masterclass in modern transportation. But the engineers weren't done copying nature. To fix the noise generated by the train's overhead power connectors, they looked at another bird, the owl. Owls fly in total silence because their feathers have serrated edges that break up rushing air into tiny, quiet currents.
Engineers copied this structure into the train's pantographs, slicing wind noise to nearly zero. They even redesigned the base of the support structures using the smooth, low-drag body shape of Adélie penguins. The Japanese bullet train proves that the most advanced engineering blueprints aren't invented in labs.
Millions of years of evolution have already solved the very physics problems we struggle with today.
The next time you face an impossible design wall, stop looking at the screen. Look out the window. Thank you for opening the archive today. Subscribe to Beyond the Blueprint, and I will see you in the next file.